2 is an eigenvector. 7 minus 7 here also. Any number here and the negative here, what happens is that people try to use the lowest numbers. The lowest is 1. Now this vector is not normalized. Normalization of vectors means that the norm is equal to 1. So it means some people like to normalize the vectors in this way. This is my first eigenvalue is -1, and the first eigenvector is 0, 1, -1. I can write like that, or I can write like j minus k, or I can write in the way how it appears there. These three notations are equivalent. They are equivalent. You study that. This one particularly, you should have studied somewhere. Now, some people like to normalize the vectors. It means that if I multiply the vector by itself, like this, I should obtain 1. This is normalization. But this vector, if I multiply, it doesn't give me 1. It gives me 2 actually. This is 1 plus 1 equal 2. So in order to normalize the vector, I have to divide by 1 divided by the square of 2. This vector is normalized now. Because when I multiply these two, this will give me a factor of 1, 2, divided by 2, divided by 2 is 1. So some people like to present the eigenvector. You will see in some textbooks that the first eigenvector, they can present like that, but also the normalized, the unitary one, let's put like that. They will display like 1 root square of 2, 0, 1, minus 1. This is a normalized eigenvector. You have seen normalized vectors? Yes, you have seen that the whole time. When you have a Cartesian plane, x and y, sometimes you draw the vectors. There's a unitary vector here and a unitary vector there. And any vector you draw as a combination, j plus k, 3, 1. These guys were unitary vectors, so you know them very well. So it's optional to display like this. It's more elegant. But you can also just leave it like that. Just leave it like this. And this is also a valid eigenvector corresponding to the first eigenvalue. Now you repeat the same operation for the others. You repeat the same operation. The second eigenvalue, what is the second eigenvalue? 2. Second eigenvalue is 2. Then you have to repeat the same story. A, B, the second vector, second eigenvalue, second vector. The matrix again is 2, 0, 0, 0, 4, 5, 0, 4, 3. The vector x, y, z. The second eigenvalue is 2, so it's 2 times x, y, z. Like that. Then you display the equations. The first equation is here. Let's put the second. Well, they didn't do the second, but we will do the second here. They didn't do it. We can do it here. For lambda 2, the first equation will give me 2x equal to x. 2 times x equal to x. So x, so this doesn't give me anything, basically. So x is arbitrary somehow. The second will tell me for y plot 5c equal to y. So if I move y to the left, 0, equal to here. So anyway, y is minus 5 to c. This relation. And the third equation for y plot 3c equal to C. Then it's 4y equal minus C. Let me check something here. 2, 0, 0, 4, 5, 4, 3, 2, 2. Dos, 2y, 4y. Oh, this isn't necessary for this one. So the first value of x is arbitrary. The first value of x is arbitrary. It will give me x arbitrary, so I will put x probably 1. The second, there is a constraint, which is 4y by c with y. If there is 4y with c equal to c. So the point, you can solve these two, and you can find the values, and y and c here. And then you find the second, and so on. But I will advertise something. I will advertise something here for you not to find desperation, because I don't want you to find desperation. This, I will show you now, right now, that you can use the software for calculating this in a moment. Then if I go again to my magical Wolfram cloud here, because of course I know that I'm no professor for developing these equations, and then, well, but I will show you here that you can find here in the documentation this one. In the documentation, you can find eigenvalues. And always there are redundancies in these calculations, because there is always two columns repeating and so on. So some people get confused with that sometimes. You can calculate the eigenvalues of any matrix here. For example, this matrix, let's put this matrix, the original matrix. Guys, silent, please. Silence. I listen many voices. Kindergarten, please. 0, 4, 5. And the other is 0, 4, 3. Evaluation. Well, let me see. Evaluate cells. These are the eigenvalues of this A, 2, minus 1. Well, let me see. I copy correctly monthly matrix. 2, 0, 0, 0, 4, 5, 0, 4, 3. Yeah. Yeah, the first eigenvalue was minus 1 for them, the second was 2, and the third one is 8. So it's correct. Now, I can also calculate eigenvectors here. Let me see. Eigenvectors. Eigenvectors can be calculated. For example, I could just copy and paste this order, and I copy this matrix again and calculate the eigenvectors. You can see that this is the one we calculated. You remember? 0, minus 1, 1. This was the one they calculated. The other ones are 0, 5, 4. This is the one I was calculating here, actually, because the first component was arbitrary. Let's say the equation doesn't give anything. the second again, the third eigenvector will be 1, 0, 0. Of course, I didn't calculate this one, but they correspond to these eigenvalues here. Of course, you have to define to which eigenvalues this corresponds this. There is a chance that by hand, if you calculate by hand, there might be errors, of course. There might be errors. But that's why we have the software for checking to us. And at the end of the day, the important is the interpretation. The interpretation you give to that. Now, let me, determinant. The determinant of a matrix can be calculated also here. Probably it's matrix operations, matrix operation. But you can see that you don't have to do all the process. The software will give you immediately the eigenvalues and eigenvectors. Determinant should be here, transpose, symmetrize, determinant here. You can calculate the determinant of a matrix like this. Let's calculate the determinant of this matrix, for example. Determinant, evaluation, evaluate cells, minus 16. This is the determinant of this matrix. But I am just calculating for completeness. It's not part of the exercise, just for showing. So now we have the eigenvalues, and we can calculate the eigenvectors corresponding to those eigenvalues. Of course, I use the software because I have doubts in the second calculation, which there is some inconsistency, I think. It gives you something trivial. Basically, the first equation gives you 2x equal to x is a 0 equals 0. So x arbitrary. The third equation is 4y plus 5c equal to y. So this is 2. Y is minus 5 to c. And the final equation is 4y plus 3c. This is just for me because I want to see something. Then for y, say 4. If I divide this, something weird happens here. Anyway, I will revise that part, but I will send you the solution by hand later. What? These vectors, this is what I wanted to explain. These vectors, I explained before, but let's put it here. This vector are showing me the axis of symmetry of my data. Let's say when you collect the data, normally, let's assume you have two variables only, x and y, two variables. And you have your data spread somewhere, and then that data gives some plots, maybe like this, I don't know. Or maybe some ellipsoid, I don't know, whatever. These axes are symmetric, or let's put it the other way around. The data is symmetric with respect to the eigenaxis, to the eigenvectors. It means when I calculate the eigenvector of this data, one vector will point in this direction, symmetric. That's why these axes are called principal axes for the data. And the other should be maybe, if you made it orthogonal, you can make it orthogonal, should be like this. Yeah. So this data is symmetric with respect to this axis. And why that's important? Because sometimes you transform your data